16.3 talks about the fundamental theorem of line integrals. It includes path independence, conservative vector fields, potential vectors, potential functions. So, given a vector field, f of x, y, we say this vector field is conservative, or if it's given in differential form, we say it's exact. Exact and conservative means the same thing, where p and q have continuous first partial derivative on the domain, then throughout D, del crossed with f, and if you recall, del crossed, and that is the partial of q with respect to x minus the partial of p with respect to y equals 0, or those are simply equal. Either or. Depending on which book you use, you could see this in so many different forms. You know, some books use just this. But instead of memorizing, take the partial of this with respect to x, the partial, just take del crossed with f and see if you get 0. If you do, you're in good shape. Otherwise, you're done. So, determine whether this is, and by the way, the word conservative comes from physics, really. That means the field in which the principle of conservation of energy holds. So, determine if the given vector field is conservative. Well, let's see. If I take del crossed with f, that is the partial with respect to x, the partial with respect to y, 2x plus 4y, 2x minus 2y, that would be a 2 minus a 4, which equals a negative 2, which doesn't equal 0. So no, this is not a conservative vector field. And if I go for this, again, if I take del crossed with f, partial with respect to x, partial with respect to y, ax plus by, and bx plus cy, that would be the partial with respect to x, the partial with respect to y, that is 0, so yes. Now comes the fun part. If f is a vector field defined on some domain D, and f is f sub x, f sub y for 2 dimensions, f sub z for 3 dimensions, I meant, you know what I mean. F is pq for 2 dimensions and r for 3 dimensions. Del f is the partial derivatives. So, to find this for some scalars on f, of f on D, then f is called a potential function. They're going to mention a potential function. Either they tell you straight to find it, or they say find the potential function. First they say, determine whether or not the field is conservative. If it is conservative, find the potential function. Later on they say just find the potential function. You don't have to check if it is conservative or not. And now we know, I just worked this out. That's the previous problem. That's right there. We know this is conservative. So from the previous problem, we know this is conservative. Now what? Now we need to work our way. We need to take this and set this equal to del f. We're trying to find this function in which if I apply the gradient on the function, I'll get this. So that's f sub x, f sub y. So you start either way, it doesn't matter. If I start with, let's say, f sub x, the partial of f with respect to x equal ax plus by, because the I must equal the I. And if I integrate, and remember, I am undoing a partial derivative. So f of xy should equal, integrate with respect, that's ax squared over 2 plus bxy plus a function of y. Why a function of y? Because when I take a partial derivative, if I had f equal ax squared over 2 plus bxy plus 3, or 3 plus y squared, if I take f sub x, that will be ax, that will be by, and that will be a 0 whether it's a 3 or a 3 plus y squared. So that's something you have to keep track of. Now, just like we did in calculus, you need to find the g of xy and you're done. Like the constant, kind of like when he said it was ax squared over 2 plus c, and now you want to find c. Well, guess what? We used the first batch. We said this equal to this. Now, you're going to use all of them. If I take the partial with respect to y of my answer, the partial with respect to y, that is 0 plus, with respect to y, that's bx plus g prime of y. That should equal the j component. That's the key. Now, if it's conservative, you'll notice a lot of those cancel out. So if I integrate, the g of y would be cy squared over 2 plus some constant k. So if I replace that by it, I'm pretty much done. If I say f of xy is actually ax squared over 2 plus bxy plus, instead of g, it's cy squared over 2 plus k, that is a fine answer. They could do this in the book. Or they could even set it equal to 0. It doesn't matter. This is fine for what we need. We just need to find a potential function because we're going to use it for something else. Here's another problem. Determine whether this is... And we didn't test this one, did we? No, that's different. Okay, so let's see how that works. So to check, first I take del crossed with f, del crossed with f, and see what I get. That is the partial with respect to x, the partial with respect to y, y squared minus 2x squared, y plus 2x. By the way, I forgot to mention, this is my function that if I take the gradient of that, I will get the vector field. And you could test it every time. So if I take the partial with respect to x, that is 2, the partial with respect to y, the partial with respect to x, that is, I forget the y. Y plus 2xy. Partial with respect to x, 2y, minus the partial with respect to y, 2y, that's 0. So that is exact. Okay, what that means, why am I squishing all of this? I have no clue. If I take del crossed with f, partial with respect to x, partial with respect to y, y squared minus 2x squared, and y plus 2xy. So the partial with respect to x is 2y minus the partial with respect to y, 2y, that is 0. It is exact. Now what? I'm going to need to find f such that if I take the gradient of f, that is f sub x, f sub y, it will be exactly this. So I start, and it doesn't matter, I always start with the first, you could do it any way you want. If I took a partial derivative of a function and I got y squared minus 2x squared, if I integrate again, you're undoing a partial derivative, keep that in mind. So the function f of xy is going to equal xy squared minus 2x cubed over 3 plus a function of y. Find the function of y and you're done. How are you going to find the function of y? Take a derivative with respect to y of this, that is 2xy that's a 0, plus g prime of y, and that should equal the j component. That should equal y plus 2xy. Those cancel out. If you integrate, g of y would be simply y squared over 2 plus a constant. So I could say f of xy, the potential function, plus k, or I could just put k equals 0. The book does that. Now, if I take the partial of this with respect to x, so if I take the gradient, let's go that way. If I take the gradient of this f, I will get the partial with respect to x. That's y squared. Bring the power down, subtract 1 from the power, plus 0. The partial with respect to y, that is 2xy. That's a 0, plus y. And you'll notice, there it is. So, find me a function in which if I applied the gradient on the function, I will get the vector field. Now here they're making the condition that it has to be conservative. It doesn't have to be conservative, but conservative has certain applications. Here, if I take the gradient crossed with f, that is in 3 dimensions or more, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and that is 2y plus 3z, 2x plus z, and 3x plus y. And if I take the gradient of that, I'm looking for the 0 vector. The I component, that would be the partial with respect to y minus the partial with respect to z. The j component, the partial with respect to x minus the partial with respect to z. And the k component, the partial with respect to x minus the partial with respect to y. So, guess what? I am getting the 0 vector. Exact or conservative. In differential equations, they call this an exact equation. Not to worry. And that's why sometimes they take this and set it equal to k. You don't have to worry about that. Well, for now, what? I'm going to set this equal to the gradient of f. So here, there's a bit more work. And I could start with the first. I could say always let f sub x equal 2y plus 3z. And if you integrate, undoing a partial derivative with respect to x, f of x, y, z will be 2xy plus 3xz plus a function. Remember now it depends on 3 unknowns. If I take a partial with respect to x, any function of y and z will zero out. Meaning, if f was 2xy plus 3xz plus 5, then the partial with respect to x will be 2y plus 3z plus 0. What if I made that plus y squared? That's still plus 0. What if I made that plus z squared? That's still plus 0. So you have to take into account the worst case scenario, and that's the only part you have to worry about. Now, I'm going to use the second. I could go in order, it's up to you. If I take the partial of this with respect to y, the partial of this with respect to y is 2x, that's a 0, plus the derivative of that with respect to y. And that should equal the j component. So the partial with respect to y equals z. If you integrate undoing a partial derivative with respect to y, I'll get g of yz to equal zy plus a function of z. So now, this just became zy plus a function of z. And it's going to always take this much work just to get that answer. Now my answer modified a bit. Now I use the third, and that is if I take the partial with respect to z, that's going to equal 0, 3x plus y plus g prime, because that's only dependent on one variable, and that should equal the z component, which is 3x plus y. Those cancel out and those cancel out. If g prime of z equals 0 and you integrate, then g of z is simply a constant. So f of x, y, z would be 2xy plus 3xz plus zy. You could write plus k where k is a constant. The back of the book will always make that a 0, and that's my final answer. Okay, if we continue on, I was going to make another video, but it seems I'm going to finish in about 7 to 10 minutes. Let C be a smooth curve given by a vector, where t is bounded between a and b. Let f be a differentiable function with continuous gradient such that you could find a potential function. Then when you want to evaluate the integral of f dot dr, remember f dot dr is work, something that we do a lot. It's f of r of b minus f of r of a. So you're evaluating, instead of figuring out the integral along f, the c of f dot dr, you're evaluating the potential function, if you could find it. Show that the differential forms in the integrals are exact. So what does that mean? That's something that comes up. This is really what you need to read out of it. And dot it with dx, dy. That's f, and that's dr. So, if you look at this, y squared minus 2x squared, right there, and y plus 2xy. So from example 2b, from example 2b, we know the potential function is given to be 2b. The potential function is xy squared minus 2x cubed, xy squared minus 2x cubed over 3, xy squared, yeah, and plus y squared over 2, plus y squared over 2. So we did this already. All what we have to do here is figure out that this is f of 3, 3 minus f of 1, 2. That's all. What's f of 3, 3? That is 3 times 9, 27, minus 2 times 3 cubed, 27 divided by 3. Is that right? That's 9. Plus 9 halves. That is 27 minus 18 plus 9 halves. That is 9 plus 9 halves. All over 2, 18, that's 27 halves. Right? Yeah. If I didn't make a mistake, that's what it is. And f of 1, 2 would be 1 times 4, that's 4, minus 2 times 1, 2/3, plus 4 over 2, which is 2. So that would be 6 minus 2/3, all over 3. 18 minus 2 is 14. So that would be 27 over 2 minus 14/3. And that would be it. Instead of figuring the path and how this works and None of that stuff. You could just take f of b minus f of a if you could find a potential function. We did part B as well. Part B is really example 2c. Example 2c, 2y plus 3z, 2, yep, and 3x plus 2y. From example 2c, I'm going to get the result. We got f of x, y, z to equal, and what did we get? 2xy plus 2x plus 3xz. 2xy plus 3xz plus zk plus zy. So again, when they give it to us in this form, you really gotta read f. I mean, if this wasn't example 2 part C, then you have to find the potential function, right? And that is 2y plus 3z, 2x plus z, 3x plus y, dotted with the x, dy, dz, something you should always look at. That's my vector field, that's my dr. Well, this is going to be f of 2, negative 1, 4 minus f of 1, 2, 3. So f of 2, negative 1, 4 is going to be 2 times 2 times negative 1, negative 4. 3 times 2 times 4. 3 times 2 to 8, 24. If I make a mistake, that's just make sure you understand the concept and how it's done. Y times z is a negative 4. So that is negative 8 plus 24, 16. And f of 1, 2, 3 would be 2 times 1 times 2, that's 4, plus 3 times 1 times 3, that's a 9, plus 3 times 2, that's a 6, that is 10, that's 19. And there it is. One more to go. So this is the whole thing. Find a potential function for the vector field and evaluate the integral. Again, this is work. If they say find the work done along this path, there it is. So how would you do this? Well, we need to find a couple of things. So potential function first. Let's see. And we don't need to check if it's exact. It didn't ask for that. We are going to set this equal to the gradient of a function, which is f sub x, f sub y, f sub z. So we start any way you want. I always start with the first. F sub x is twice the cosine of y. If I integrate, this is my answer. That is twice, so I'm undoing a partial derivative with respect to x. That is twice x, the cosine of y, plus a function of y and z. If I could figure out what this is, I'm done, and that's where the most work is. Now, if I take a partial derivative with respect to y, it should equal this part. If I take the partial derivative with respect to y of my answer, that is negative 2x, the sine of y, plus g sub y of yz, and that should equal this component, 1 over y minus 2x sine of y. Those drop off, and if I integrate, I'm doing a partial derivative with respect to y, I will get g of yz to equal natural log of, and they're all positive, so I could say y instead of absolute value of y, plus a function of z. So now I'm going to take this out and replace it by natural log of y plus h of z. Almost done. And now, if I take the partial of this with respect to z, which is, that's a 0, that is a 0, that's simply h prime of z. That should equal the z component. The k component, I'm sorry. And if you integrate, this is a traditional with respect to z, h will equal natural log of z plus k. Absolute value, z is always positive, I mean the absolute value. So now I could take h and put natural log of z. So this is what I got. I got my potential function to equal 2x the cosine of y plus natural log of y plus natural log of z. There it is. Now, if you want to take the integral of f dot dr, right, along c, that's going to simply be from 0, 1, 1 to 1, 2, 6. That's going to simply be f of 1, 2, 6 minus f of 0, 1, 1. Well, what is f of 1, 2, 6? F of 1, 2, 6 is twice the cosine of 2 plus natural log of 2 plus natural log of 6. Okay, whatever that is. That is twice the cosine of 2 plus natural log of 12. Right, combine the two logs, minus, what is f of 0, 1, 1? That is 0 plus natural log of 1 is 0, natural log of 1 is 0. So that's my answer. And you might be asking, but wait a minute. You didn't take this into account. Well, the points are on it. I didn't take this into account because you're gonna read a couple of things on your own and figure out what that means really quick. So if you look at, suppose c sub 0 and c sub 1 are two piecewise smooth curve path that have the same initial and terminal point, then the integral along either path is the same, provided that the gradient is continuous, right? And the integral of f dot dr is independent of path, which means it doesn't matter which path you take, if and only if this integral equals 0 at every closed path. And you should refer to the book to see what is the meaning of closed, simple, simply connected, and open. Again, they come up in definitions. There's no specific homework on it, and you're not going to be tested on it, but it's going to come up in a lot of the definitions. And there we are.